This will be a walkthrough of the AQA GCSE Chemistry 2022 Higher Tier Paper 1. Question 1. This question is about metals and non-metals. Figure 1 shows an outline of part of the periodic table. So the figure is given to us. A, B, C and D are labelled with different parts of it. Element Q is a dull solid with a melting point of 44 degrees Celsius. Element Q does not conduct electricity. Which section of the periodic table in figure 1 is most likely to contain element Q? So we have to remember how the periodic table is arranged. It's arranged into two parts, really metals and non-metals. So all of our part A are metals, all of our part B are metals, some of our part C are metals, and some of it are liquid metals, and part D are non-metals. So let's look at the properties of element Q that they told us. They told us a dull solid. So that could apply to A, B, C, or D. It has a melting point of 44 degrees Celsius, which is quite low. So that will rule out A and then will rule out B because they're metals, so they tend to have a higher melting point. So we're left with part C and part D. Let's read on. Element Q does not conduct electricity. So remember I said that C contains some metals also. So those metals are most likely going to conduct electricity, such as mercury. So D is most likely to be the correct answer because D contains our non-metals, which we know are not going to conduct electricity. So the answer should be D. Element R forms ions of formula R2+ and R3+. Which section of the periodic table in figure 1 is most likely to contain element R? So what do these small little numbers tell us with the positive sign? It tells us that they are going to form positive ions. And we know that metals should always form positive ions. So our non-metals are forming negative ions, so then that means it cannot be part D. But A is showing us really group 1 and 2. And we know that if elements are in group 1, they tend to lose one electron, so become a positive ion. But B are our transition metals. So that means that they can usually form multiple compounds with different charges. So our answer for 1.2 should be B. 1.3. Give two differences between the physical properties of the elements in group 1 and those of the transition elements. So we know that group 1 is going to be in section A of our periodic table above, and in our transition metals are in section B of our transition metals. So how are the physical properties of anything in A and B going to be different? Well, when we're talking about physical properties, we can't talk about how they're reacting. So we shouldn't be thinking about terms like reacting faster, more bubbles, because those are the chemical properties. We want to think about physical properties such as boiling point, melting point, soft, and things such as that. So what can we remember about our transition elements? Or transition elements, they are going to be hard metals, whereas our group 1 elements are going to be soft metals, meaning that you can cut them easily. So we can say that group 1 elements are going to be softer. That's definitely one difference. Remember that we're using our comparative language ER to signify that we are comparing. A second difference, well, we could start to talk about the melting of the boiling point. Again, with our transition metals, they're going to have higher melting points. So if we talk about in terms of group 1 elements, so group 1 elements will have a lower melting point. There are other options that we could say. Thinking about them a bit carefully, we could say things about what they could do. So our group 1 elements, they're really used in terms of structural things, whereas our transition elements, they can sometimes be used as a catalyst. So we could say for another option, just in case you're asked to write another one, group 1 elements not useful as catalysts. Question 1.4. Complete figure 2 to show the electronic structure of an aluminium atom. Use the periodic table. So we're thinking about the element aluminium. We need to use the periodic table to help us. So by looking at the periodic table, we can see that aluminium is in group 3. So the group number reminds us how many electrons are in the outer shell. So if we're in group 3, aluminium, it'll have 3 electrons. You can use a dot or a cross to denote that. So 3 crosses in the outer shell. The numbers in our periodic table remind us of how many protons are there, the atomic number. But the atomic number also can tell us the number of electrons, because it should be the same as the number of protons. So aluminium has an atomic number of 13. So that means we should be drawing 13 crosses in total. But we need to use our rules for how many electrons in each shell. So maximum number of electrons in the first shell is 2. Then it should be 8. And then in our next shell, 8, and so forth. So we need to put 2 in the first shell. So right now we've got a total of 5. So we need to get to 13. So that means we need to put another 8 in the second shell. Question 1.5. Aluminium is a metal. Describe how metals conduct electricity. Answer in terms of electrons. 3 marks. So we're thinking about metals and metallic bonding, because that's where we understand the concept of conducting electricity also. So our understanding with metallic bonding is you have positive metal ions surrounded by a sea of delocalized electrons. So let's use that to start formulating our answer here. Positive metal ions with a sea of delocalized electrons. But we haven't spoken about the conducting electricity. So what does the word delocalized mean? It means free to move. So if the electrons are free to move, what are they able to do? They're able to carry the charge. And they can carry the charge through the structure. Please be careful, you cannot say throughout the structure. It must be through the structure, because we're not thinking about the whole metal itself. We're thinking about how these electrons are able to just move. So electricity or the current or the charge is able to pass through the metal. Question 1.6. Name the type of bonding in compounds formed between metals and non-metals. So non-metal and metal is ionic bonding. So it's got to be ionic. Question 1.7. Magnesium oxide is a compound formed from the metal magnesium and non-metals oxygen. Describe what happens when a magnesium atom reacts with an oxygen atom. You should refer to electrons in your answer. So once again, we need to focus on electrons. So magnesium oxide, if we write the formula for that, that is MgO. So what does this tell us now? It tells us that an ionic bond is formed between magnesium ion and an oxide ion because it is ionic bonding. So we need to remind ourselves what's going to happen with this metal, what's going to happen with this oxygen. So magnesium is in group 2. So that means it's able to lose 2 electrons because it is a metal. Metals always form positive ions. Oxygen is a non-metal, so that means it's going to gain 2 electrons. This forms magnesium Mg2+ and oxide O2- ions. And what we can just say to make sure is what the ionic bond is. It's an electrostatic attraction. So we've definitely referred to the electrons in our answer. We've mentioned what happens to the magnesium atom. We've mentioned what happens to the oxygen atom. And we've stated the ions that are formed. And that should get us our 4 marks. Question 2. Sodium carbonate reacts with hydrochloric acid in an exothermic reaction. The equation for the reaction is shown. A student investigated the effect of changing the mass of sodium carbonate powder on the highest temperature reached by the reaction mixture. Plan a method to investigate the effect of changing the mass of sodium carbonate powder on the highest temperature reached. Okay, 6 marks now. So this is to do with our required practical to do with temperature change. So we've got to, again, when thinking about a method, recall the variables. So independent, dependent, and control variable. So reading the information just here, below the equation, and again reinforced in the question, we're able to figure out what our independent variable is. So that word change is helping us figure out the independent variable. So that will be the mass of sodium carbonate powder. Our dependent variable, again, can also figure it out from reading the information here. So we are going to have to measure temperature, or specifically the highest temperature of the reaction mixture. So if we're going to be changing the sodium carbonate powder mass, and we're going to measure the temperature that's reached the highest of this reaction mixture, we now need to think about, if we change anything else, will that affect the temperature that we measure? So let's go to our equation. we know that we're going to be changing the mass of this. But we've got another reactant in the equation, hydrochloric acid. The information given to us here doesn't tell us anything about the hydrochloric acid, so we need to mention it. It's aqueous hydrochloric acid, so a solution. So what properties would a solution have that we want to be aware of? Its volume and its concentration. So we definitely want to keep those the same. The volume of hydrochloric acid we need to keep the same. And the concentration of hydrochloric acid we need to keep the same. Okay, perfect. So before we finally write our answer, let's also think it's an investigation. So what are some of the things that we need to consider when we're working scientifically in some sort of investigation? We need to think about what pieces of equipment we're going to use to measure. We need to think about what sort of variables, again, we are going to be measuring with those pieces of equipment. And we need to think about how we can make our results valid. So we're a bit clear on these variables. So let's look at our information here and then think about our equipment before we start. So the mass, what could we use to measure the mass? That's definitely got to be a balance. So we have to mention balance somewhere. Temperature. Manually, we use a thermometer. So we'd have to mention that. Volume of hydrochloric acid. There are different pieces of equipment that we can use to measure the volume. The easiest one we can mention would be a measuring cylinder. So definitely have mentioned 3 pieces of equipment that is important in trying to do this properly. And then how can we make sure our results are valid? Well, the easiest way is by repeating the investigation. You will have to repeat the investigation because we're going to be changing the mass, so we need different masses. But we want to make sure that each time that we change the mass, that value that we get of that highest temperature is somewhat reliable. So we would have to mention repeating the investigation at the same mass of sodium carbonate. So let's begin. Use a balance to measure a certain mass of sodium carbonate powder. I'm just going to use the formula just to make things a bit quicker. Measure a certain volume of hydrochloric acid with the measuring cylinder. Now what we haven't mentioned before is where are we going to have this reaction mixture in? We have to think again that we are going to be trying to measure the temperature that the reaction mixture reaches the highest. So we want to try and keep all that heat energy, because it is an exothermic reaction as it says. We want to keep all that energy in the container that our mixture is going to be in. So we want something that's going to be a good insulator. So thinking back to your required practical, the best piece of equipment to hold our reaction in is going to be a polystyrene cup. So add sodium carbonate to the polystyrene cup. What we're able to do now, and you could add the hydrochloric acid before that, is we need to check the temperature. I'm going to check the temperature at the start of the experiment. So measure starting temperature with a thermometer. Now we're ready to add our hydrochloric acid to the cup. What we want to do now is we want to stir the mixture. So they will definitely all of our sodium carbonate reacting with all of our hydrochloric acid. We then want to record the highest temperature that the reaction reaches. Then we can say repeat investigation with the same mass of sodium carbonate. And what we can say is repeating this investigation twice, and then we can calculate a mean. Now we know we've done it 3 times, we can calculate a mean, able to exclude any anomalies if we need to, and then we can say repeat investigation with an increased mass of sodium carbonate powder. So there is our answer, and we've covered everything that is going to enable us to get our 6 marks. Figure 3 shows a line of best fit drawn through the student's results. So it's given us a graph. On the x-axis, it's labeled with mass of sodium carbonate in grams. On the y-axis, it's given us the highest temperature reached by the reaction mixture in degrees Celsius. 2.2. Determine the gradient of the line of best fit in figure 3. Use the equation gradient equals the change in highest temperature divided by the change in mass. Give the unit 5 marks. So we know that our gradient normally is going to be the change in the values on our y-axis divided by the change in the values on our x-axis. So we need to use the graph to figure that out. Our line is straight, so we do not need to worry about the tangent. So what we can do first is try and get our unit. So we saw our x-axis was measured in grams, our y-axis was measured in degrees Celsius. So that will mean our unit will be degrees Celsius per gram. So we've already picked up a mark. Let's try and figure out the gradient. So what we can do, because the line is straight, is we can just take 2 points on our line and we can find out what are the values for those 2 points on the x and the y-axis. So let's just take the last and the first point to make it easy. And we need to just read off to those axes and find out what they are. So for our first point, our lowest point, reading to the x-axis, it is 1 gram. For our highest point, reading off the x-axis is 5 grams. So the difference there will be 4. So we know when we do our gradient or calculate it, it's going to be dividing by 4. Let's find out for our change in y now. So let's figure out what the scale on our y-axis is going up in. You can see that that value in the middle is 23. So that means that each line is going up 0.2 each time. So that first point for our y-axis should be 22.2. For our highest point now, let's do the same. So we've got 3 lines for our point after 28. So that should be 28.6. So to find the change in our y value is going to be 28.6 minus 22.2, and that should give us 6.4. So to calculate our gradient, that is going to be 6.4 divided by 4, which should give us a value of 1.6. So 1.6 degrees C per gram is our gradient. Next question, 2.3. The initial temperature of the reaction mixture is where the line of best fit would meet the y-axis. Determine the initial temperature of the reaction mixture. Show your working on figure 3. So we need to do something on our graph now to figure out what the initial temperature of the reaction mixture is going to be. This first sentence is extremely important. So going back to our graph now, we need to find out what will be the temperature when this line hits our y-axis. So we would need to get a straight line that is going down to our y-axis. We already know that at 1 gram of sodium carbonate, our temperature is 22.2. So what we would just need to do then is do 22.2 minus 1.6, and we will get our initial temperature. So plugging that in, it should be 20.6. Question 2.4. Another student repeated the investigation but added sodium carbonate until the sodium carbonate was in excess. Which sketch graph shows the results obtained when sodium carbonate was added until in excess? Tick one box. Okay, so let's look at this first graph. So in this one, the temperature is increasing faster because our line is becoming steeper. Well, let's think about what's actually happening. In our second one, the line is the same almost as what was in our previous graph. In our third one, still have our straight line, but then it becomes horizontal afterwards. So let's think about what's going on, and then we should be able to get the right answer here. So some sodium carbonate was added to our hydrochloric acid, and we get a temperature change. But when the sodium carbonate is in excess, maybe what's going to happen, and most likely is going to happen, is that the hydrochloric acid is going to be saturated. How do we know that the hydrochloric acid is going to look or be saturated? Well, in our container, we have our hydrochloric acid, and then we might start to see a solid lump appearing at the bottom of our beaker or container. And what that would be, in this case, it would be the sodium carbonate, as it can't be dissolved anymore. So if the sodium carbonate can't be dissolved anymore, then we shouldn't really see a change in the temperature. So looking at our graphs here, the one that shows no change in temperature after excess sodium carbonate is added is C. Figure 4 shows a reaction profile for the reaction of sodium carbonate with hydrochloric acid. So we've got a reaction profile. So what do our reaction profiles tell us? They tell us many things. They can tell us if a reaction is exothermic or endothermic. It can also tell us the activation energy. And it can also tell us the energy change. So what do labels X and Y represent on figure 4? Well, X is showing us just the energy. It should be nothing else, because it will tell us the energy of the reactants, it will tell us the energy of the products, and then from there we're able to work out anything else. Y, well, label Y showing an arrow between the reactants and the products. So if our energy in our reactants is here, and the energy in our products is here, then this Y is telling us the energy change. So 2.6, how does the reaction profile show the reaction is exothermic? Well, exothermic means energy is given to the surroundings. There is one way in which our energy profile can show us this an exothermic reaction, and that is using this. Exo equals RAP. Reactants above products. So if you look at the line for the reactants, so our energy for reactants is greater than our energy for our products. or you could say the energy in our products is below the energy in our reactants. So either one of those is fine. Question 3. This question is about different forms of carbon. Figure 5 represents the structure of diamond. Okay, it's giving us a key, solid circles representing carbon atoms. Describe the structure and bonding of diamond. Okay, 3 marks. So, you remember that carbon is a non-metal. So the only atoms that are in this structure are non-metals. So if that's the case, then these lines, which are between our carbon atoms, can only be one type of bond, which is covalent. So we have to be talking about covalent bonds in our answer. So 1 point we can straight away say is that this structure has many covalent bonds. Now, what we can also think about is the size of this, because if we take an element such as chlorine, that has covalent bond, but it's a small structure. This, you can see, has many different carbon atoms, many covalent bonds, so we can call this a giant covalent structure. Now, what's special about this diamond, if we really think about diamond, it's quite strong, quite hard. So what provides that strength? It is those covalent bonds. So we can say that the bonds are strong. And then lastly, let's look a little bit carefully at the structure more. The other thing that we can talk about is the number of bonds. So let's take this carbon atom here in the center. How many bonds is coming from this carbon atom which I've circled? 1, 2, 3, 4. So let's take another example. There's 1 bond, 2, 3, 4. So we can describe that by saying each carbon atom is covalently bonded to 4 others. If I didn't say that the structure has many covalent bonds, then we could say that it has a giant covalent structure, and that can also give us a point. 3.2. Explain why diamond has a very high melting point. Well, we can take a point from above now, and it's going to help us. We can take this point here, the bonds being strong, and we can put that in our answer below. Why? Because if it's talking about high melting, you want to think about going from then solid to liquid. So that will mean that bonds need to be broken. So the covalent bonds are strong. So if it's talking about high melting point, the temperature in which it's going to turn from a solid to a liquid is going to be high. So a lot of energy then, because that's what the heat is providing, is needed to break the bonds. And we picked up our 3 marks here. 1 for mentioning the bonds are strong. The second one for mentioning that the bonds need to be broken here, and the energy, which is a lot, is needed to do so. Figure 6 represents the molecule C70. What is the name of this type of molecule? 1 mark. So recalling our structure, again, another giant covalent molecule here. So the correct answer should be fullerene, because graphene has different layers. A nanotube will be more in the form of a tube, and polymer will be repeating units of monomers. So fullerene is definitely our answer here. 3.4. Molecules such as C70 can be used in medicine to move drugs around the body. Suggest one reason why the C70 molecule is suitable for this use. Okay, so we're talking about medicine to move drugs around the body. So what is it that we would want in order for that to happen properly? Well, if it's going to move around the body, maybe traveling the blood, reaching cells. So we definitely don't want this fullerene molecule to be causing more damage to our body. So one of the properties that we would want for our C70 is to be non-toxic. But if we had to give another option, a reminder that it's only asking us for one reason, another reason which would be important is that the C70 would be a small molecule because it would need to travel around our body. But if it's a small molecule, that means that it will have a large surface area to volume ratio. You could also say that the C70 is unreactive, because all we want this molecule to do is to provide a drug and move it around the body. We don't want it to interact with anything, which could cause further problems. Calculate the number of C70 molecules that can be made from 1 mole of carbon atoms. The Avogadro constant is 6.02 times 10 to the power 23 per mole. Right, 3 marks. So, information that they told us then is 1 mole of carbon atoms. Now, what is 1 mole of anything equal to? It will be Avogadro's constant, so 6.02 times 10 to the power 23. So, we have a molecule that has 70 carbon atoms. So what we need to find out here is if we have got 1 mole of carbon atoms, we want to find out how many molecules of carbon 70 can be made from that mole of carbon atoms. So, first thing that we could find is the number of moles of C70 molecules. And the easiest way for us to do that is just taking 1 and dividing that by 70. And we'll come out with a value of 0.01 remain recurring. So, our next job now, because we now know the number of moles of these C70 molecules, is we now need to times that by our Avogadro's constant. So multiply our number of moles, 6.02 times 10 to the power 23, and then we will be able to find out how many molecules we can make from it. So the number has to be less, because we're trying to take some atoms and build them to make this carbon 70. So if you're finding an answer which is greater than 6.02 times 10 to the power 23, it's not correct. So multiplying these two together should come out with 8.6 times 10 to the power of 21. Question 4. This question is about zinc and compounds of zinc. A student produces of zinc chloride by reacting zinc oxide with hydrochloric acid. The equation for the reaction is shown. Student adds zinc oxide to hydrochloric acid until the zinc oxide is in excess. Give one observation that the student could make to show that the zinc oxide is in excess. So one observation, meaning one thing that they can see to determine, okay, the zinc oxide is in excess. So it's similar to the previous question when we were thinking about sodium carbonate. If we take a container, add some hydrochloric acid, keep adding zinc oxide until it is in excess, we would tell that by a solid appearing at the bottom of our container. So we would want to say that a solid forms at the bottom of the container. That indicates that the zinc oxide is not being dissolved anymore. Next question, why is zinc oxide used rather than excess hydrochloric acid? Well, we put zinc oxide in, it doesn't dissolve anymore, and then we would do a step to make sure that we are just left with our zinc chloride, which is an aqueous solution. So the next thing that we would do logically after we do this, because this is again a required practical for crystallization, the next thing we would do would be to filter it. So if we were to continuously add hydrochloric acid, then we wouldn't be able to filter that properly. We'd have to use a different separation technique to do that. So the reason why we use zinc oxide is because it can be filtered. And if you want to be a bit more careful with your answer, you can say and separate it easier. Question 4.3. Name one other compound that a student could add to hydrochloric acid to produce zinc chloride. So we still have our hydrochloric acid here, so that's fixed. We're still going to form a zinc chloride, so that's fixed. But it's asking us, what could this also be, but still produce zinc chloride? So we've got to think then about another compound that contains zinc that can still give us this zinc chloride. Well, this zinc chloride is a salt, so we need to think what other compounds can still produce some salt. Well, think about what other type of neutralization reactions you can have. The other ones that you can have, because we have here metal oxide plus hydrochloric acid. The other one we could have is with a metal hydroxide. So our metal hydroxide then in this case would just be zinc hydroxide. One more, it could be zinc carbonate. Right. So 4.4. Describe how the student could obtain crystals of zinc chloride from a solution of zinc chloride. 2 marks. So we're briefly having here to describe the process of crystallization. So we've got a solution of zinc chloride. We should be able to assume that it's already been filtered. So what would the next logical step be to ensure we can get crystals? We would transfer this to an evaporating basin. We would then heat up that evaporating basin. So the first thing that we would have to say is heat the solution. So our first point then would be to heat the solution until it evaporates. But we won't form crystals just yet. There's a very important last step that we must do, is then leave the solution to dry or cool, and then crystallization will definitely happen. You'll form your salt crystals. Zinc chloride is also produced in the displacement reaction between zinc and copper chloride solution. The equation for the reaction is shown. 4.5. Complete the ionic equation for this reaction on mark. So we have our zinc, which is just there. We then have got a gap to put in something, and then zinc 2 plus, which is contributed from this part of our reaction in our products, plus something also. Well, ionic equations, when we do them, we are trying to show what has been oxidized and what has been reduced. So in this case, we don't have to worry about our chlorine or chloride here. So that is not important. So that means that in these gaps, we should be looking for copper to be included. The chloride doesn't change in the reaction, so we don't need to include it. So we would need to put a Cu here and Cu here. However, we now need to think, how will we show the coppers being changed? Let's look at what happens to the zinc first, because the ionic equation is also an example of a redox reaction. And redox means reduction and oxidation occurring in the same reaction. So let's see what's happened to the zinc. It started off as metallic zinc, so it has no charge, no number next to it. It then goes to form Zn2 plus. So if it's a positive, that means it's lost electrons. And if you remember our oil rig, oxidation is loss, reduction is gain. So this is showing us oxidation here. So that must mean that when we are trying to show the change for copper, we need to show reduction. So, as we said, reduction is gain of electrons. Let's look again at the equation that's given to us at the beginning. We can see that we've got metal copper here. So that means that this copper is going to be the same here. So that means we cannot be putting any charges for this copper. So this is fine. We have to change this somehow. So if 2 electrons have been lost from zinc, that must mean that 2 electrons are being gained by copper. So we would need to put a 2 plus next to copper. Why is zinc described as being oxidized in this reaction? We just explained it. Zinc loses 2 electrons. .7. Zinc and copper can be used with another substance to produce electricity. Complete figure 7 to show how zinc, copper, and another substance can be used to light a lamp. Label zinc, copper, the other substance used. The symbol represents the lamp. 3 marks. So, how could this be related to something that we have learned? Well, when we're thinking about producing electricity and we are thinking about the inclusion of metals, our process which we have learned is electrolysis. So we have to be thinking about this process in order to pick up some marks. So what is the principles of an electrolysis setup? Well, there should be a positive and a negative electrode. Negative electrode called the cathode, a positive electrode called the anode. Those electrodes have to be placed in an electrolyte, and the electrolyte should contain some compound which has ions which are free to move. So in this case, our other substance is probably going to be our electrolyte. So what we can do is we can add a container showing some liquid, and we can label that with our electrolyte. And if we wanted to, could probably give an example of an electrolyte. So a nice example of an electrolyte can be copper sulfate. So our ions would be freely moving in this container, but they would need to interact with the two electrodes. So our electrodes should be going into our electrolyte, and we just need to label them with what they're asking us. So we can label this one as zinc and this one as copper. Labeled zinc, labeled copper, label the other substance used, which is the electrolyte.